All right, welcome back. We're going to keep going from where we left off, and we will finish up shortly. All right, a quick digression into the textbook. I'll just read this slide. The textbook spends a lot of time discussing this topic, and I didn't want to discuss it too much, but it's definitely worth mentioning. I've already talked about it a lot, but I'm going to beat the dead horse one more time. As we've already begun to see, it truly does not matter which point we use in each subinterval to determine the height of our rectangle. I could throw a dart into each subinterval with a blindfold and pick the point that the dart lands in each subinterval to determine the height of my rectangles, and we would still get a good approximation as long as our rectangles are thin enough.
Okay, yeah.
Additionally, it doesn't even matter if our subintervals are all the same length. Our approximation will still be good as long as the largest subinterval, which remember we said that was the norm of the partition, gets small enough.
Perfect.
In this course, and as the textbook does later, I simply choose the approximation method that is the easiest. Equal subintervals, choose the endpoint of each subinterval to be what determines the height of the rectangle, because all approximations are valid, so it makes sense to choose the easiest one.
Yeah.
The bottom line is, I don't want you to think that this is the only way we can get a good approximation. We can pick random intervals and random points on those intervals and still be able to arrive at a good approximation. Additionally, and this is the point I really want to nail home, all approximations, no matter how we construct them, approach the true area under the curve as long as our rectangles get smaller and smaller.
Okay.
No matter how absurd we construct them. All right? Well, within reasonable bounds. As long as our rectangles are getting smaller and smaller, it's going to approximate the area. It's going to approach the area under the curve. In other words, if we have infinitely many rectangles, for all of our approximation methods, we're going to get the true area under the curve.
Yes.
Cool. Let's keep going. The definite integral. Remember how we said that the sum will approach the true area under the curve if the rectangles are thin enough?
Yeah.
Well, then mathematically, we can say the area under the curve is truly equal to this Riemann sum.
Cool.
I don't know why it says n. It should be I. I put this on Desmos, so that's my bad. I took a screenshot of me writing this on Desmos. This should say I. But all it is our Riemann sum, right? But our n value, our subintervals, is infinity. We have infinitely many subintervals.
Yeah.
So this sum is going to tell us the true area under the curve.
Got it.
Cool. Any questions?
No, all good.
The number we would get is called the definite integral of f over interval AB.
Okay, cool.
Cool. Awesome. Any questions?
No, all good.
Cool. Theorem, all continuous functions are integrable. That is, we can find the area under the curve of any continuous function. Kind of what we were talking about, right? We assumed that our function was continuous, and we went through all of this stuff, and we said as long as the function is continuous, we can find the area under the curve easily. Yeah. So this is kind of one of those intuitive theorems.
Yeah, for sure.
Cool. Any questions?
No, all good.
Cool. Last two slides, I'm just going to talk about integral notation, and we'll be done.
Right. Okay, cool.
All right. So we write this. So here is our Riemann sum, right? It writes it a little differently. It writes the limit as n goes to infinity of this, right? You could replace the n with an infinity on the top, and it would be saying the same thing, right? So do you see how this is the same thing as what we said before with the infinity on the top?
Yep.
Okay, cool. So this is equal to this, all right? And this is integral notation. This is the integral from a to b of our function times dx. And we'll explain what that means in a second, all right? Okay. So this is the notation we use to describe integrals, the area under curve. And we're going to kind of break it down in the previous slide. All right, so notice how in the sum we use f of x sub I and delta x. But here we use dx and f of x. So our notation kind of changes a little bit. You see what I'm saying?
Yep.
I'll do a little quiz. Why do you think when we talk about integrals, when we talk about infinitely small rectangles, why do you think we use dx instead of delta x to write for our notation?
Because it's like again back to the getting infinitely small. It's
exactly.
Not just the change. It's like an infinitely small change.
Exactly. So do you see how why it makes sense to replace the delta x with dx to let people know that in this scenario, we're dealing with infinitely small subintervals.
Yes.
Additionally, we replace our f of x sub I with just f of x. All right, and I'll explain why in the slideshow in just a second. Here we go. All right, we write f of x instead of f of x sub I in our integrals, even though our Riemann sum, had f of x sub I. This is because you can imagine as our rectangles get infinitely small, we're no longer using a choppy selection of x coordinates, right? When we're doing our approximations, we select choppy selections of x coordinates to determine our height, right? But as our rectangles get infinitely small, we're not using a choppy selection, but rather a continuous unbroken sampling of all the x values from A to B to find the height of our infinitely small rectangles.
Okay.
Hence, we replace xi with x to let people know we're kind of like we're taking the values from all the points on the function to act as heights of a rectangle. All right?
Yeah.
Also, notice how it does not matter what variable we use. If x were t, u, g of x, whatever the heck we wanted it to be, the integral will be the same. Let's go to, this is kind of what we were talking about a while ago. All right? All right? If we graphed f of g of x with respect to g of x, all right, the function we get would just look like f of x, right?
Yeah.
I think you suggested that earlier in the year, and you said it made sense. Does it still make sense to you?
Yeah, it totally makes sense. Like,
Okay.
If it's g of x of f of x, then only f of x is being applied to the input g of x.
Exactly. So the function will look like f of x.
No, it makes perfect sense.
Additionally, if our input was t and our function was f of t, all right, the graph would look the same.
Yeah.
So in integral notation, right, we could say the integral from a to b, the area under the curve from a to b, of f of g of x dg of x, all right, is the same thing as the integral from a to b of f of x dx, all right? Because if we drew f of x with respect to x and we found the area under the curve, it's the same area under the curve as f of g of x with respect to g of x.
Yeah, okay.
So as long as these two variables are the same, all right, the actual value we get for the integral is not going to change.
Yeah.
So it doesn't matter what variable we use when we're doing integrals. We're going to get the same area under the curve.
Okay.
As a result, and this in the last slide will take 2 seconds. Okay. Because of this, we often call the variable of integration a dummy variable. Mathematicians are super harsh and mean. But we call it a dummy variable because it doesn't matter what variable we use. Okay. The integral we get would be the same if it was f of t dt, f of g of x dg of x, whatever. And we kind of showed why that's true. All right. Let's look at this picture right out of the textbook. All right. And you don't have to remember what these mean. You can either just take a picture or we can come back to it, whatever. The little elongated s thing is called the integral sign.
Yep.
The bottom thing is the lower limit of integration. That basically means where do we start integrating from? And the upper limit of integration is where do we end integrating from? So this is the integral from a to b. We start integrating at a and end at b.
Okay.
The function, the area, the function whose area under the curve we're trying to find is the integrand. And x is the variable of integration.
Okay.
You can think we're integrating with respect to x.
Yes. All
right. If it was g of x or t, then we'd be integrating with respect to t. We're integrating with respect to our input. So we call it the variable of integration. All right. The whole thing is called the integral of f from a to b.
Okay.
And that's the area under the curve of f from a to b is the integral of f from a to b.
Yeah.
When you find the value of the integral, you have evaluated the integral. So if someone said, evaluate the following integral, that would mean find out what it's equal to.
Yeah.
And we don't know how to do we don't know how to do that yet. Everything we've done is just purely hypothetical. We still don't know how to find the true area under the curves. We've kind of hinted that, well, if we hypothetically made infinitely small rectangles, we get the true area. But we still don't know how to do that yet. All right.
Yeah.
And disclaimer, we're not actually going to use that method to find the true area under the curve. But it's still important to understand that if we could somehow figure out what that sum would be with infinity at the top, that would give us the true answer, the true integral.
Okay, cool.
Okay. So yet again, we don't know how to calculate integrals just yet, but we at least hypothetically know if we had infinitely small rectangles, we could do it.
Yes.
Cool. All right. I ran out of space in the last slide, LOL. Last couple points. Notice how the integral sign looks like an elongated S. This is to emphasize that the heart of integrals is summing up many infinitely small quantities, the S standing for sum.
Okay, cool.
All right. If you recall back to the beginning of class, I mentioned how the second branch of calculus talked about adding up many small quantities together to get the answer you want. Remember how like at the very beginning of class, as in like the first lesson, I said the second branch of calculus is adding up many small quantities to get an answer you want.
Yeah.
This is why integral calculus is exactly that at its core. All right.
Yeah.
It's also why we call it integrals. All right, because we think of integrals as adding up many small, infinitely small rectangles. We're integrating all the values of those integrals. We're bringing them together.
Yeah.
That's why we call them integrals.
Cool.
Yeah. So at the beginning of class, I said that integrals are the area under the curves. That is true, but we're also going to continue to think of integrals as adding up many small quantities together to get the answer we want.
Okay, yes.
That's going to become useful in Unit 7. All right, next we'll do later. And yeah, so the next parts we'll do tomorrow.
Okay.
Yep. All right, so tomorrow we're going to finish this up, finish this lesson up and start the next lesson. And tomorrow I'm going to plan to do the 2 mini units, which covers the fundamental theorem of calculus and how to find integrals. And if we get through all of that, that'd be great. And then the last topic we have to cover is basically the last unit is super weird. It tells you different ways to approximate the area under the curve that aren't rectangles, which is fine. But I don't know why the textbook includes it. But I guess we'll talk about it just in case it's something you have to know.
Okay.
But the next 2 units, in my opinion, pretty much finish up the basics of integrals.
Word.
Right. And similarly to how we had a unit on derivatives and then we had a unit on applications of derivatives, Unit 7 is going to be applications of integrals.
Okay.
And Unit 6 is a quick digression into differential equations, which you'll see when we get there why it was important to learn integrals before we did that. Okay, cool. So I'm going to end the video for YouTube. Thank you guys for watching. I'll see you guys in the next video.